Video I'll be looking at the conservation of kinetic energy. In the last video, I talked about the conservation of linear momentum that for a system of colliding bodies, their total momentum is always constant, provided there is no external force acting on the system of colliding bodies. That means when two bodies collide, momentum is simply transferred from one body to another since their total momentum is always conserved. And then from the principle, we have that the sum of the momentum of the two bodies before collision is equal to the sum of the momenta of the two bodies after the collision. Now, this is the equation of the principle of conservation of momentum. Now, but you can see that in most collisions, we may have the idea of their initial kinetic energy. Let's say you are given this. This is the first ball. Let's call this ball A. This is B. And this one has mass m2. This one is traveling towards the other one with mass, with speed u2. Now, these two velocities may be known in most cases. But after the impact, let's say the collision is elastic, how do you start finding their final velocities, v1 and v2? This may be difficult to know because there are two unknowns here, v1 and v2. So which means you need another equation. And that equation must come from the conservation of kinetic energy. In some collisions, kinetic energy is conserved and as well as momentum. Such a collision is called elastic collision, and other collisions, kinetic energy is not conserved. And the kinetic energy that is not conserved, meaning that there's a loss of Ke before and after the impact. The loss of Ke is therefore converted to other forms of energy like sound and heat energy. Of course, I'm sure you know when two bodies collide, there's usually a sound that is heard. Sometimes, okay, that sound is a form of energy. It comes from the loss of Ke. And sometimes there is what we call deformation. The two bodies will be deformed. And energy is needed to deform an object, to deform a body. So that energy is also coming from the loss of Ke. And at the end, you discover that the total energy is still conserved, even though kinetic energy is not conserved. So whether the condition is elastic or inelastic, total Ke is always conserved. And we can write the kinetic energy like, for conservation of Ke, we are saying that the sum of their Ke is before collision, m1u1 squared plus half m1v u2 squared is equal to sum of their K is after collision, half m1 v1 squared plus half m2 v2 squared. Okay, now we are going to deal with these two equations. I call this my equation 1 and call this my equation 2. Now this goes, I have m1 u1 squared plus m2 u2 squared is equal to m1 v1 squared plus m2 v2 squared. Okay, now what I want to do, let me take equation 1. From equation 1, I'm going to write that m1 u1, I'm bringing this term here, m1 v1. Let me bring the momentum of the final and initial momentum of the first body is equal to this will have m2 v2, okay, minus m2 u2. That is from equation 1. I bring my m1 v1 this way. I'll take my m2 u2 the other way. So I have this m2 u2. Okay, so I want to factor out m1. m1 into what? u1 minus v1 is now equal to m2 into v2 minus u2. I count this my equation 3. Okay, now let me take this equation 2 and then rewrite it so that I rewrite it the way I did this one. I'm having m1 u1 squared, bring this term here, minus m1 v1 squared is equal to have this term there, m2 v2 squared, bring that term there, m2 u2 squared. So just like I did to equation 3, let me factor out m1 still. So let me come to this space. I have some space here. So I have m1 into u1 squared minus v1 squared, okay, is equal to my m2 into V2 squared minus U2 squared. Okay, so what I have in the bracket is more like difference of two squares. So how do you simplify, evaluate difference of two squares? We have m1 into this becomes u1 plus v1 times u1 minus v1. So that's how we factorize difference of two squares. That gives us m2 is equal to m2 into v2 plus u2 times v2 minus u2. Okay, that is factorizing difference of two squares. All right, so let's call this equation 4. So look at the two equations, 3 and 4. I want to divide now equation 4 by equation 3. So when dividing equation 3 by 4, or let's say 4 by 3, what do I have? I'm going to divide this equation by this. Okay, so let me write it out. m1 into u1 plus v1, u1 minus v1 is equal to m2 into v2 plus u2, v2 minus u2 divided by, I have m1 into u1 minus v1 equal to m1 m2 rather into v2 minus u2. Okay, so m1 cancels this m1, this one cancels this, and then this cancels this. So what is left after cancellation? I have u1 plus v1 is equal to v2 plus u2. Okay, let me bring the initials together. Bringing the initials together, I have u1 minus u2. Check very well. I'll bring u2 to this side, bring v1 to the other side, is equal to v2 minus v1. Okay, what do we conclude from this expression, this equation? From this equation, we can conclude that for a perfectly elastic collision, the relative speed of approach of the two bodies is equal to the relative speed of separation of the two bodies. Now, this is the initial speed, and the u1 minus u2 means their relative speed. v2 minus v1 means their relative speed also, but this one is after collision. This is before collision. Okay, so I'll call this one equation 5. Now, this equation is very helpful in solving the unknowns velocities after collision. Velocities of the bodies after collision is v1 and v2. And I'll still have my equation 1 again, m1u1. I'll still come back to this, plus m2u2 is equal to m1v1 plus m2v2. So these two equations, that's my equation 1, will be very essential or needful in solving the unknowns, that is v1 and v2. Okay, so how do we find v1 and v2? Let me take from equation 1, or let me say from equation 5. Can I multiply equation 5 through by m1? Okay, so if I multiply this by m1, I have m1 u1 minus m1 u2 is equal to m1 v2 minus m1 v1. I guess you know what I've done. Multiply equation 5 through by m1. So I have m1 u1 minus m1 u2 equals m1 v1 minus m1 v2. So I call this equation 6. So what I want to do now is to add equation 6 to 1. That is, solve these two equations simultaneously. I'm going to eliminate one term. So when I add the two equations together, I'll have this plus this gives me plus. I'll factor out u2 because u2 is common into m2 minus m1 is equal to, now if I add these two, m1 v1 minus m1 v1, these two will cancel out. What is left is v2 into m1 plus m2. Okay, now I'm looking for v2. Can I make a v2 the subject of the equation? So I have v2 therefore equals 2m1 u1 plus u2 into m2 minus m1 divided by m1 plus m2. Okay, so recall that this m1 plus m2 is dividing both terms of the numerator. That gives me v2 is 2m1u1 over m1 plus m2. Then plus dividing this again, I have m2 minus m1 over m1 plus m2 times my u2. Okay, so this is how we find v2, from the two equations. The first equation and this other equation we just derived using the kinetic energy and the momentum conservation equation. I want to find v1 now, okay? So I move to another page. To find my v1, I'll start by recalling equation 5, that is the relative speed of approach or the two masses equal the relative speed of separation of the two masses. I'll multiply this by m2, that is equation 5 by m2. So I have m2u1 minus m2u2 is equal to m2v2 minus m2v1. Okay, so that is that. Then from equation 1, m1u1 plus m2u2 is equal to m1v1 plus m2v2. So what I'll do is to subtract these two equations. Okay, now this minus this gives me, because you can see that if I subtract this from this, u is common. I can factor out my u and have m2 minus m1 multiplied by u1, which is common. Subtract minus this gives you minus 2 m2u2 is equal to, come back here now, m2v2 minus m2v2, that is 0. So what I have left is minus m2v2 minus m1v1. That will give me, okay, you can see that v1 is common rather, into, maybe I can factor out the negative here, because it's negative here, into m. Okay, I guess you are following. So because I have minus m2v1 minus m1v1. Okay, so factoring out the negative gives me minus v1, which is common, into this plus this. So that when I multiply this by negative, it gives me negative sign 2. So I want to take off this negative sign, multiply 2 by negative. Multiply this by negative will make this one minus m1 minus m2 plus m1 into u1. Multiply this by negative makes the sign positive. So m2u2 is equal to v1 into m2 plus m1. Okay, this can be, you can switch these two to give me m1 minus m2 times u1 plus 2m2u2 is equal to v1 into m2 plus m1. Dividing both sides by m2 plus m1 gives me v1 equals m1 minus m2 times u1 over m2 plus m1, then plus 2m2u2 over m2 plus m1. Okay, that gives me the expression, the equation for calculating v1 and v2. Okay, let me repeat the equation. This is my v1, and the one I did before, I got v2 as 2m1u1 over m1 plus m2. Then I have plus m1, m2 minus m1 rather, over m1 plus m2, that is times my u2. Okay, you can see very clearly that v1, each of them is expressed in terms of the initial speed. v1 is this and this minus this over this times the initial speed u1 plus this is my 2m2 over m2 plus m1, or I can make it always, because m2 plus m1 is the same thing as m1 plus m2. Okay, I can decide to switch these two masses and write it as m1 plus m2. So you can see that the denominators are the same for both m1 plus m2, m1 plus m2, m1 plus m2, m1 plus m2. And you can see that this one too has u1 as well as what u2. So with this, you can find the two speeds. Let's take an example